Every major smart contract platform operating today relies on a strategy of adaptation. Networks deploy rapidly by lifting battle-tested tools, like the Ethereum virtual machine, or borrowing general-purpose compiler infrastructure like LLVM and WebAssembly adapters. This pragmatism accelerates initial development, but it carries a severe, unavoidable cost. Networks inherit the structural limitations of the systems they adopt. Take the Ethereum virtual machine. It is a stack-based sequential execution engine built for a different era of computing. It treats state storage as a flat key value space. Because of this, the compiler cannot optimize data access patterns because the virtual machine completely obscures them. This design forces strict sequential execution. The EVM has no mechanism to prove that two separate transactions are independent. To maintain safety, it must execute them one at a time, even if they touch entirely different parts of the network state. WebAssembly chains attempt to solve this with near-native execution speeds. But WebAssembly was designed to run inside web browsers. It lacks native concepts for blockchain state, and it has no understanding of transaction boundaries. To function as a blockchain, WASM platforms must wrap their engines in heavy runtime adapters. They have to actively inject gas metering and manage state through external APIs. The result is a dense wall of indirection, separating the compiler from the runtime. The industry's current parallelization ceiling is a structural bottleneck. Forcing a sequential virtual machine to perform dynamic dependency resolution at runtime limits throughput to the speed of a single core. SynapticChain operates on a different logic. If the compiler already possesses all the necessary information about state access, the runtime should not expend resources discovering it. This requires an operational model known as S=0, or schedule at time zero, resolving all transaction dependencies before execution begins. Legacy systems discover dependencies dynamically through runtime locks and tracking, creating friction. S=0 strips those mechanisms out completely. By executing pre-organized plans, S=0 enables lock-free deterministic parallel execution. The heavy lifting moves entirely into the compilation pipeline. The core challenge in blockchain execution is scheduling. The system must determine the precise order of transactions and identify which ones can safely execute in parallel. Current execution models approach this three ways. First, strict sequential execution leaves multi-core hardware unutilized. Second, optimistic parallel execution. Conflicting transactions force the system to roll back, burning cycles discarding work. Third, runtime analysis adds bottleneck overhead directly to the critical execution path. All three models fail to maximize hardware because they force the runtime virtual machine to act as a traffic cop rather than operating purely as a dedicated execution engine. To remove the traffic cop from the runtime, the compiler must generate a map of every contract's dependencies. This process starts by enforcing explicit state in the type system. By declaring variables with the state keyword, developers transform storage from opaque data points into tracked locations that the compiler natively understands. The SynapticChain parser digests this explicit state, taking raw source code and translating it into an abstract syntax tree. Within this tree, the compiler can now distinguish simple scalar values from complex, multi-layered nested maps, mapping the exact topography of the data. By making state explicit, the pipeline turns storage from a runtime black box into a statically analyzable blueprint. The dependency analyzer then takes over, walking the syntax tree to identify every read and write operation. It traces method calls to route storage slots, forming a directed acyclic graph. The scheduler uses this graph to assign independent operations into discrete parallel execution lanes. For state conflicts, the scheduler enforces strict deterministic rules, ensuring every validator reaches the exact same execution order. Finally, the code generator compresses these parallel lanes into a Borscht.plan file, which is 90% smaller than verbose EVM bytecode. When the virtual machine receives this compact plan, it performs zero interpretation and has absolutely no dispatch overhead. It acts as a strict, simple loop, executing the precompiled operations exactly as instructed. The execution engine operates with minimal runtime overhead because the plan file dictates the parallelization strategy before the first cycle of computation begins. Legacy virtual machines use fixed opcode pricing. This creates economic distortions, charging users high, rigid fees for operations that require minimal network resources. This table breaks down SynapticChain's per-operation gas pricing. The network prices operations individually. A complex map set costs 20,000 gas, while an arithmetic compute operation costs a maximum of 30. Executing a persistent state mutation carries a much higher cost than a simple arithmetic calculation. Furthermore, state safety and re-entrancy protection are established natively. The dependency analyzer guarantees them by construction at compile time, eliminating the need to write fragile runtime safety checks. When gas metrics and safety protocols are derived directly from static compiler analysis, protocol economics align with the actual physics of the hardware. SynapticChain targets high-frequency DeFi protocols. For standard NFT mints or basic token transfers, others suffice. But for automated market makers operating multiple independent pools, the system provides the parallel execution required to function at scale. In enterprise environments, the compiler enables sub-500 millisecond finality and native ISO 2022 support, standards that sequential chains cannot physically reach. In large-scale IoT supply chains, tracking thousands of independent devices scales linearly with hardware core counts because the compiler proves their data accesses are distinct before the transactions run. This matrix outlines the architectural divergence. While legacy networks spent over 8 years building workarounds to parallelize the EVM, SynapticChain achieved operation-level parallelism and compile-time scheduling in 17 months by working from first principles. Established platforms possess maturity, but SynapticChain trades that maturity for architectural correctness. It proves that to reach the highest tiers of network performance, developers must leave the virtual machine behind.